So what do we do when we have to integrate a function or evaluate an integral that u substitution doesn't work for? Well, this trick of integration by parts is the next trick we try. And you always set it up so that you have one of the products is going to be some u function, and the other function, the other part of the product, the other factor, is going to be the derivative of some function. And then you want to write down this formula. We want to memorize this. We have to have it down pretty well. Okay, so here's the first example they've got worked, and they've got it all worked out for us. Where you have x is some function times the cosine of x, and we have to find the antiderivative of this. So what we do is we have to decide what is u and what is dv. So one way to remember this in this mnemonic is that if you look at your functions that you have, these are the order that you want to choose to let a function be u. And if you have a logarithm, let that be u. And then if there's no logarithm, if you have an inverse trig function, let that be u. Or then if there's a polynomial, you want to choose that to be u. And then if there's an exponential, let that be u. And then if you have a trig function, that's the last thing you're going to choose to be u. So what you can do is one of these functions has to be u, and the other function that you have is going to be dv. And as you can see is what they've already worked out. They said, okay, so I've got a polynomial and I've got a trig function. So polynomials come before trigs for our u, so I let the u be x and the cosine x dx, the other part of that integral, be dv. And then what you're going to do, what you want to do is make why this helps is you want something that you can take the derivative very easy, and the other thing has to integrate very easy. Because what you have is a blank. We're going to have x, and you're going to have cosine x dx. And that's when you start. See, you don't know the rest of the stuff. So then if you take the derivative of the x, you get dx. If you take the antiderivative of cosine x dx, you get sine x. You have that set up, and I'll kind of walk you through here what else he shows is, see, the formula says you take u times v. So once you've got u and v, you're going to go u times v, and that's what goes first. So that's why they wrote down here. They wrote here. He wrote x times sine x. See, x times sine x. The u times the v went there, and then it's minus the integral of the v function times the du function. So you just multiply that, and that gives you the new integral, and you factor out constants, as you'll see, and everything. Now this is, again, we got another integral to deal with, but that's really easy to integrate. The antiderivative of cosine of sine is negative cosine, and a negative negative turns out positive, and then don't forget the c. Okay. So to check our work, what we can do is we can take the derivative of the result and see if that actually works out and gives us that original integrand that we're trying to integrate. So I've got a product, the derivative of, so the product rule is the first times the derivative of the second, plus the second times the derivative of the first, which is 1. And then I would take the derivative of cosine, which is negative sine. And then, of course, the derivative of c is a constant. So that cancels out, and that is what we started with. So that was the correct integral. So here we go with another example. They're warning us to make sure that the normal u substitution doesn't work. Well, I don't know. If we let u equals e to the x, the derivative of u is e to the x. That doesn't work. And if we let u be x, we still get a u there. That's not going to happen. So this is a place where we're going to use integration by parts. So then I got to decide, what am I going to let be u? Well, polynomials should be u before exponentials. So we're going to let x be u, and dv is going to be e to the x dx. So now what's nice about this, the derivative of x is just dx. The antiderivative of e to the x is e to the x. So then if we use that formula, remember it's u times v minus the integral of v du. So I'm going to go u times v, get e to the x, x e to the x, minus the integral of e to the x dx. So now I'm going to do the antiderivative again, and that's nice because the antiderivative of e to the x is e to the x. So x e to the x minus another e to the x plus some constant c. Now sometimes on a multiple choice test, they might write this integral this way, factoring out a e to the x. But typically they won't. Now the next part of this question asks us now, instead of an indefinite integral, we're going to evaluate this function. So I've got x e to the x minus e to the x, and then I don't know if I've stressed this with you, I don't need to worry about the c with an indefinite integral. And here's why. I mean a definite integral. Because if I drop in 1, that's going to give me 1 times e minus 1. 1 times e minus e plus c minus 0 right? 0 times e to the 0 is still 0, minus e to the 0, which is 1, plus some constant c. And when you distribute this stuff through, look what happens. Well, the e's are gone, and I've got a c plus 1 minus another c. That constant cancels off, so all I'm left with is the 1. So this is why when we're evaluating back in Chapter 5, when we used the fundamental theorem of calculus, we didn't worry about c because it just cancels off. To write the general solution, you need to include it. When they ask you to evaluate a definite integral, we do not need to use the c. So now we're looking at this, and I see a polynomial and a log. And a log is the first thing I want to let be u. So I'm going to say u equals ln x. I'm going to say dv equals, you have a space to write this, I realize now, x squared dx. So now the derivative of the ln is 1 over x dx. The antiderivative of x squared dx is 1/3 x cubed. And then you got to remember it's going to be u times v. And I'm going to write the polynomial first. 1/3 x cubed times the natural log of x minus the integral. Remember, we're going to do v times du. And what's kind of nice about this one, I've got 1/3 x cubed times 1 over x dx. Well, one of those x's cancels off, so that leaves me x squared, and I've got a constant. I've got that 1/3 constant. So I'm just going to pull that out in front. I'm going to write that as x squared. I've got a dx. And then, let's see, can I move this up? I don't think so. So I got to squeeze it in here. So this is going to be so what I remember, what I do is 1/3, negative 1/3, times, so I'm going to add 1 to the 2, make it be 3, divide by the 3, so that's 1/3. So what's going to happen is I'm going to get 1/3 times 1/3 to 1/9. So I'm going to try to write this up here. 1/3 x cubed ln x, that should be cubed, minus 1/9 x to the 3rd plus some constant. Now I believe this is a typo. I believe this goes to the next question, so I'm going to ignore what's written here. So we've got to do evaluate this, and if we remember that mnemonic lippet, logarithms is supposed to be u, so all I'm going to do is I'm going to write ln x is my u, and I'm just going to have dx be the dv. Now if you need to, you can write a box or you can label it in. So now I'm going to take the derivative of ln. I get 1 over x dx. The antiderivative of 1 dx is just x. So then using the rule, it's going to be u times v. So I'm going to write x times ln x minus the integral of, well, let's see, x times 1 over x. All of that cancels out just to be 1. So I'm just times 1 dx. Well, the antiderivative of 1 dx is x. So the natural log of ln x minus x plus some constant. It always amazes me that the derivative of natural log is so easy and the antiderivative is such a mess. And what Stu Schwartz is trying to point out here is if you choose the wrong u substitution, the wrong decision for u and dv, and if you, in other words, if you forget about lipit and use the wrong thing, here's what happens. So I'm going to take the derivative of e to the x, get e to the x dx, take the antiderivative of x, well, that's 1 half x squared. So then I'm going to write 1 half x squared, so the u times v, minus the integral. I can pull the 1 half out in front, but then I've got x squared e to the x dx. Now what's supposed to happen with this second integral is that's supposed to be an easier thing to do, and it's getting more complicated. So we obviously went the wrong way. And that's what's going to happen when you start looking at these integrals to evaluate. You're going to make a wrong decision, and if it isn't getting easier, you went the wrong way. So let's see here. So here's one. Let's see, where can I write this? I'm going to come over here. So they're saying to make sure you choose wisely. Kind of like the Indiana Jones movie, right? With the Holy Grail? They didn't choose wisely and they died. So if you remember lipit, I see the 2 is a constant, so I can pull that out. And I'm just realizing that they set me up here. So let's do it. Let's try this. So the integral of 2 x e to the x squared dx. Well, if I let the polynomial come first, so x is going to be u, e to the x squared is dv. Well, x is easy to take the derivative of, but how the heck do I get the antiderivative e to the x squared? That seems hard. So if it's too hard, we're going to do the Ed Berger method and do something else. So then, if you're looking back at this, you'll see that it says, this concludes that the integration by parts is the wrong tool. It is. They just want us to try u substitution. So if we think back to that work you just spent all of last week or this last week doing, if we say u equals x squared, du equals 2x dx, and boy, I'm seeing I've got a 2x, I've got a dx, so that'll all be du. So really what I'm going to integrate is e to the u du, and what could be easier? So the antiderivative of that is e to the u plus some constant, and of course we said that u is e squared, so e to the x squared plus c. Boy, a lot easier than integration by parts. So example 5, and I'm going to write down lipid again. All I'm seeing is an arctan x and a dx. Well, let's see. The I stands for inverse trig function, so that's what u should be. So the arctan of x is u, dx is dv. The derivative of arctan, I don't know if you've got this memorized yet, but 1 plus x squared. And the antiderivative of dx is just x. So if we do u times v, that leaves me x times, I'll change the writing of arctan to that form, minus the integral of x over 1 plus x squared dx. Now I'm sure you're thinking, I don't really want to use integration by parts with this next problem, this next integral, but if you notice, you did this in 6.2. If you let u be 1 plus x squared, du is going to be just 2x dx. And if I divide by 2, that leaves me, because I don't see a 2 in this integral anywhere, well, other than the exponent. So I'm going to divide by 2 to make it 1/2 du equals x dx. So that means I can pull that 1/2 out in front. I'm going to integrate u du over u, because remember I can let the x dx be du, or 1/2 du, and I brought the 1/2 over here. So now to finish this, the antiderivative of 1 over u is ln. So x arctan x minus 1/2, and here's the thing that we need to be concerned about with the absolute value signs. This will never, 1 plus x squared will never be negative, so we don't need to have absolute value signs there. We'll just be happy with parentheses. Then plus c. Now the only other thing that might happen in a multiple choice kind of test is they'll make you remember, that's an exponent. I can pull that exponent in front, so they might write it this way: 1/2 ln of 1 plus x squared to the 1/2 plus c, which is the same thing as ln of the square root of 1 plus x squared plus c. They might even pull the negative up on top and make it be 1 over that square root. Okay, but so there's all variations of the same. So this is certainly an acceptable answer. We just got to be able to manipulate it. So this is probably the worst kind of integration by parts problem. Just so you know where we're headed with this, we're going to have to do integration by parts again, and then move the integral over to the other side and divide by 2. It's kind of cool the way it works. It's a little cumbersome to do. So we'll do it. We'll walk through it, and because I'm going to make you do it. So let's see. I need to decide what to use for u. Well, if we think about Lipit, I'm supposed to use exponentials before trigs, so e to the x is u, sine x dx is dv, so the derivative of e to the x is e to the x dx. The antiderivative of sine is negative cosine x. The u times v is going to be negative x cosine x. And then because it's minus the integral, and I've got a negative there, I'm just going to write plus the integral e to the x cosine x dx. Not much different from what I've started with. So let's do it again. So I'll let u be e to the x. I'll let cosine x dx be the dv. So the derivative of e to the x is e to the x dx. The antiderivative of cosine is sine. And for some reason I wanted to write cosine. So that's going to be, this part is going to be plus e to the x sine x minus the integral of e to the x sine x dx. So I took a minute to rewrite this. So here's my original integral that I had to evaluate, and here's what I've got after my 2 integration by parts. What I want you to notice is that this integral is exactly the same as that integral, except it's the opposite sign. If I take a minute, I add this to the other side, doesn't that give me 2 integrals of e to the x sine x dx? So that means, and this is technically not here anymore, right, because I moved it. So that means I can divide by 2, so I can divide this mess by 2, and that is the integral for that original function. So this is what will happen if you have to do the derivative twice, the integration by parts twice, and you still end up with a mess. take a look at that original integral. It could be a situation like this where you just move it around, divide by a constant. So this video is getting long enough, so what I'm going to do is I'm going to skip over example 8 and just go to example 9, because there's another trick we can use that makes this a lot easier. So what we have here is an example 9, is we've got to see how we've got the polynomial first, and then we've got this other function, which you can do with some of these functions when they have a polynomial. Sometimes other kind of functions work too. What you have is usually one function is very easy to differentiate, and the other one, relatively easy to integrate. So what I'm seeing here is I'm going to let the x squared, and this is called tabular integration. I don't remember if I said that or not. And you just write down the two pieces. And what I'm going to do is I'm going to take the derivative of the x squared. And I'm going to go, so that becomes 2x, and that becomes 2, and that becomes 0. That's as far as you've got to go. Once that function taking derivative goes to 0, you're done. On the other side, we're going to integrate it. Now, we're going to do a u substitution in our head here, because I know that the antiderivative of cosine is negative sine, and then the 4x. But then if I were to take the derivative, I'm going to have that extra 4 kicking around. So I'm going to stick a 1/4 in front. Then I just keep going. Well, let's see. That's going to be... Actually, this isn't negative, is it? Now that I said that, I see that it shouldn't be negative. Now I'm going to take the antiderivative, and this will be negative. So, and then I've got another extra 1/4 coming along, so I'm going to write that as 1/16, and that's cosine 4x. And then I got to do this again, so that's going to become, let's see, the antiderivative of cosine is sine 4x, and I've got that extra 1/4, and 4 times 16 is 64, and it's still negative. Then you draw these diagonals, and then you get to alternate signs, plus, minus, plus. Then you're just going to write the products here. So I'm going to do x squared. See, what this saves us from doing is we'd have to do integration by parts 2 or 3 times to get the answer. So what this does is this just lets us do it all at once without going through that process. So 1/4 x squared sine 4x. And then I've got a minus right here, minus, so that turns to plus. And then 2 over 16 is 1/8 cosine 4x. And then 2 times negative 1/64 is what? Negative 1 over 32 sine 4x plus c. And that's as easy as it is. I mean, that's not hard. When we watch Stand and Deliver after the AP exam, you'll see this on the board. He walks them through this. And that's it. We're going to spend some time in class doing these problems, and we'll have to decide what more we got to do out of the book. Okay, hope it helps.